So, yep. What we're looking at is, again, we're still looking at matrices. Yep. Nope. So, yep. Verifying two matrices inverses and kind of talking about the inverse of a matrix. Now, when we normally solve an equation, we can normally divide by a variable or divide by a number. But with matrices, we're not able to do that. We have to take its inverse. Because there is no dividing with matrices, we take inverses instead. So the inverse of A times matrix A is 1. And we can solve with this direction here. Now, if you notice, we multiplied the inverse to the right-hand side, left-hand side. So it means that we have to apply it to the left-hand side on the other one also. So we have to kind of keep uniformity. I'll get that in a second. So we can do this here with inverses. And now, because it's coming from the left-hand side of the equation, A inverse times A, we have to take it from the left-hand side on the other side. We have to keep it on the same side of the equation for this to work. So let A be an n by n matrix, and let In be the n by n identity of the matrix if there exists an inverse such that the matrix times its inverse is equal to the identity is equal to the inverse times the matrix. It should work either direction. It's going to work both ways. Then A inverse is called the inverse of A. So when we look at two matrices here, we've got to multiply them together, both directions, to see if they are inverses. So what we're going to do is we're going to take matrix A, negative 1, negative 1, 2, 1. And we're going to multiply it by 1, negative 2, 1. And if we get the identity matrix, this here, it can't be 2, 0, 0, 2, or any other numbers. It's got to be a diagonal of 1s. Then it is the inverse. Times them together, so we're going to go over down. So this will be negative 1 times 1 plus 2 times 1. Then we're going to do it again, over down, so negative 1 times negative 2, which I'll just say is 2, plus, well, negative 2, over down. And you could type this into the calculator and done this via the calculator also. Actually, okay, I'm going to just go in and write this out. Over, down. Now we're going to go over, down, so 1, negative 1 times 1, plus 1 times 1, over, down. Now we're going to do it again, over and negative 1 times negative 2. I see, I think where I got you confused on the top one, because this should have been negative 1 times negative 2. Yes, that's where I think y'all were getting a little confused. We'll go over, down, negative 1 times negative 2. We'll do the same thing, negative 1 times negative 2, plus 1 times negative 1. So when we actually do the multiplication, so we'd have negative 1 plus 2. Here we're going to have 2 minus 2. Here we're going to have negative 1 plus 1. And here we're going to have, well, negative, so 2 minus 1. Which actually gives us 1, 0, 0, 1. So it works. There's all that. Flip them. And we do it again. Because A times B is going to equal B times A, which is going to equal the identity. It should work in both directions. Now, if it fails in one direction, you're done, because it has to go both ways. So if it doesn't go one way, it doesn't matter if it works the other direction. It's not. So we can go over, down, which would be 1 times -1, which would be -1. -2 times -1 would be +2. And we do it again, over and down. 1 times 2 is? -2 times 1 is? Over, down. 1 times -1 is? -1 times -1. And lastly, over, down. 2 times 1 is? -1. And that's it. That's all we have to do for these here. And if we want to show that two matrices are inverses, this is really all we're doing. We're just multiplying the two together, showing that they are both the identity. And that's it. Questions on this here? So, here's all this here. I have that, which is equal to this, which is our identity. The other direction. We have this identity, so as you see, A times B is equal to the identity is equal to B times A. This is an example of a square matrix that has an inverse. Note that not all square matrices have inverses. Also, it has to be square. It has to be a square matrix for it to have an inverse. It has no inverse. If it's a square matrix, then it has an inverse, or can have an inverse. If it's not a square matrix, this automatically does not have an inverse. It is not invertible. Finding the inverse of matrices. If a matrix A has an inverse, then A is called invertible, like I just said, or non-singular. Otherwise, A is singular. A non-square matrix cannot have an inverse. I normally get ahead of these slides sometimes. And really, it's pretty much if it's singular, it's not invertible, we can't do anything with it. If you notice, I think pretty much when you type these in and go through these here, it will say sing error, which means it's saying that it is a singular matrix. It does not have an inverse. Non-square matrices to C, note that order of this here, where M is different from N, it doesn't work. So if we want to find the inverse of this here, there are different methods to finding it. One method is doing it by hand, another method is doing it by a calculator, and a third method, which is frowned upon, is paying someone else to do it. So if we're doing this by hand, we say A, the inverse of A is equal to, we switch A and B, or let's see here. So given A is equal to A, B, C, D, A inverse, I don't think it's 1 over the determinant. We flip A and D and make B and C negative. Actually, since you have your book open. I'm just trying to remember the actual formula. Because I'm wanting to say there's a determinant involved, but I don't think there is. So it would make sense to introduce it that way.
I think that was it.
Yeah. Yep, okay, that's what I thought. Yep. So it is this here. Now, I'm going to rewrite it so it's not as scrunched up. But really, is 1 over the determinant of A times D, negative B, negative C, A. And this is kind of the shortcut to doing inverses. So for this here, what we would do is I'd have 1 over. Now the determinant of A is our cross. So 1 times negative 3 minus, yes, 4 times negative 1. Now the matrix part of it's kind of nice because we go negative 3, 1, those flip. The others become 1 times negative 3 is, which is, yes. Now you can do this in a calculator by putting in matrix A and saying A inverse. The x to the negative 1 is inverse. Because it is the button we use for matrices. We'll also give you the inverse. Now, I want to see, because I think they use this formula here to get inverses. In the system, okay, so they're going to go about it using a system, and we get this here. Check the results. It does work. Note to this system, we can do whatever, da 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 da. Okay, I'm going to pull the video back up, and I'm going to pause it here and talk more about inverses and what we can do with it. As we do this by hand, we end up doing our augmented moving the systems around so that we get the left-hand side to be the identity. When writing this here, consider the matrix, and we can do all this here. Inverse of a 2 by 2 matrix, which we kind of already found. And we use that formula, and that's what we use to find it. So if we use this here, we would find the determinant, which is 4. And so we would plug our numbers in. 1 over 4, 2, 3, 1, 2. Using our thing, using switching and changing signs. Multiply, and we get this here. Now for the calculator, if it gives you decimals, math, fraction, enter, will change even the matrices into fractional form. So it'll change it back to fractions. So you don't have to deal with decimals. Now here, because the determinant of matrix B is 0, it means it's a singular matrix. If the determinant is 0, then it will be a singular matrix. Systems of linear equations. Okay. Now, the way that we use inverses to solve these here, and again, we've done this before. This is all pretty much rehashing. Yes? Coming back to you. The way we set this up is a little bit interesting in that we're going to set up a matrix of the coefficients only. So we have this here, x, y, z. That would be 1, 1, 1. 0.06, 0.075, 0.09. We multiply by x, y, z because those are the variables. Because again, when we multiply, we go over, down. Over, down would give us all of this here. Now we set it equal to 10,730 and 0. So this is how we would get the problem set up and get it started. Questions on this here? Okay. Go on and plug this into your calculator. So matrix A, we're going to have is this first one here, 111.06, 0.075, 0.095, 10, negative 2. The matrix B is going to be the 10,730 and 0. This might be a little bit easier to read. A and B. We don't have to do the X one. Yep. So we have this set up here. Y'all have got those typed in, yes? Okay. Now what we can do with the calculator is, well, if we look at this as equation, AX equals B. Well, we know that the inverse of A times matrix A will give us the identity, which for matrices it would be 1. And we do that, this will just give us X over here. Now what we do to one side, we have to do to the other. Now since we multiplied it from the left, we have to keep it on the left. So we'd have A inverse times B. So in the calculator, we can do A inverse times B, matrix A inverse times B. Y'all got that typed in? Yes.
No, I got the same thing. I didn't put negative 2. I put 2.
So A inverse times B, which gave you this here. So that 15, negative 200, negative 2, negative 21.5, 300, 3.5, 7.5, negative 100, negative 1.5 is A inverse. So if we actually found A inverse first, we would get this here. Then we would multiply it by our matrix B and get 4,000, 4,000, and 2,000. X, Y, Z. And we get this here. Yep.
Why did this keep go blank?
Because that is the end of the lesson. Yeah. Homework. $574. We're not 5 through 7. Not care about those. 13 through 19 odd. 25, 28. Those look good. And that's it.